Okay, we're ready to introduce an important concept when dealing with functions. So the I can statement is for 4.2 is I can evaluate functions using function notation. So let's write the word notation right here. Function notation, and we're going to be using function notation all the time. So let's take a look at the warm-up. The warm-up says, what is a function? So remember, a function is a set of ordered pairs where each x can be matched up with only one y. Each x can be matched up with only one y. And then a reminder here, what is the domain of a function? Well, the domain of a function, those are the numbers that you plug in. So let's put what you plug in, and that's usually the x's. Whoops, that's usually the x's. And the range, that's what you get out. So what you get out once you plug something in, and that's usually going to be the y's. So because functions are such a big part of what we study in math, we use a really special type of notation to remind us that the equation we're working with is a function. So function notation looks like this. It's got an f, and then we've got a set of parentheses, and then an x right there. And we literally read this like this. We literally say f of x. So if you ever see this, we just say f of x, and everybody knows what we're talking about. Now, what is f of x? F of x is the same as y. So remember, when we plug in an x, we normally get out a y. What we're saying here is that if you plug in an x, what you get out is the function value at x. So f of x is the same as y, or in other words, y equals f of x, or this is actually the best way to write it right here. So writing f of x is equal to y, and you'll see why this is the best way to write it in just a few minutes. Now, I do want you to realize that we can use any letter we want to name the function. A lot of times we start out with f. It's just a convenient choice. It reminds us that it's a function and things like that, but there are some other letters that we'll use as we kind of roll through this. So you can think of a function kind of like a machine. It's got something that it does. It's got some math that it does. So we dump something in. So we dump a number in or an expression in or something like that. It does some math to it, and then it returns the answer to us. So x goes in, and the function value, which we call f of x, comes out. So that means the ordered pair is, instead of x and y, it's x comma f of x. So we plug in an x, and we get out the function value at that x. So here's our function machine right here. We're going to dump an x in there. The function's going to do something, and what comes out is f of x. So let's take a look at an example right here. So this is example 1. It says f of x. Again, get used to that phrase and the way we say that and stuff. So this is f of x equals x minus 3, and it says, is that a function? So we're going to check and see if it's a function. And I've got some space here in a table. I've got some space maybe over here to put some work. And then over here, we're going to kind of make a point by writing down these function values. So here's the way this works. We're going to plug in an x. So we're going to plug an x in right there. So what we're going to write down here is we're going to write down f of negative 2. Well, if we put an x, or put a negative 2 right here, we're replacing the x with a negative 2, so I'm going to put one right here also. So this is going to be a negative 2 minus a 3. So notice what we've got here. We've got the function f of x, and the function is x minus 3. So wherever there used to be an x, we put a negative 2. So we put a negative 2 right here, and we get an answer of negative 5. So I'm going to put a negative 5 right there. And again, we're just keeping track of this in a table. So the next one we're going to do is f of negative 1. Again, get used to the way we say that. So wherever there's an x, we're going to put a negative 1. So there's a negative 1 here, there's the minus 3, and we end up with a negative 4. And we just basically go through and do each one of these. So if x is 0, we're going to find f of 0. Wherever there's an x, we're going to put a 0. So this is 0 minus 3. And you can kind of catch the pattern here, what's happening on every one of these. So if I put in a 3, we put a 3 right here. We subtract 3, and we end up with 0. And this is where it gets a little bit interesting. We don't always just have to plug in numbers. We can actually plug in variables or expressions. So wherever there used to be an x, we're going to put an a, because we want to plug in an a wherever there was an x. So this is going to be f of a. So there's going to be an a right here, and then I do a minus 3. Now, the interesting thing about this part as opposed to all of these others, these all had like terms. So we had just plain old constants that we could combine. This is just an expression. It says a minus 3. So that's literally all that we can do right there. It's just a minus 3. Now, these are ordered pairs. So these are ordered pairs that we could put on the graph, and granted this one looks kind of funny. But the reason I have this over here is I kind of want to make a point and make sure everybody understands this. We said earlier that it's actually a nice way to write this to think of, instead of saying y equals f of x, to say f of x equals y. This is asking what is the function value when x is equal to negative 2. Well, this is what f of x is right here, so that would be negative 5. What is f of negative 1? That would be negative 4. What's f of 0? Negative 3. What's f of 3? 0. And what's f of a? F of a is a minus 3. And what I'd like you to focus on is this one right here. You'll notice that this is the x value that we plugged in, and this is the f of x value that we got out. Just like we have xy pairs here, you can see that this is a negative 2 comma negative 5 pair. So when we write it in this format right here, we can actually see the xy pair or the x comma f of x pair just like that. So the question here is, can you see why this is a better way to write it? I hope, because instead of an xy pair, we have an x comma f of x pair. Y is the same as f of x, so f of x is equal to y. Can go either way there. So just kind of keep that in mind. Now, function notation does take a little bit of getting used to, but it is a lot better in the end because it makes it so all we have to do is say f of 6, f of 2, and everybody knows what we're talking about. We automatically know what we need to plug in. So if we look at example 2a here, we've got g of x. So notice that the name of the function has changed. Instead of calling this f of x, we just say g of x. It's a different function than we had up above. And we want to find g of 2. So literally, to find g of 2, we're just going to put, instead of an x, we're going to put a 2. So this is 2 times 2 plus 5. So we get g of 2 is equal to, let's see, that would be 4 plus 5. So this is going to be 9. So this right here, that is the answer. G of 2 is 9. And I've got the answer over here, so if you were looking ahead, you could just see what that was. But it's nice to know how we calculate that. But I've got a question for you. What does g of 2 equals 9, what does that mean about the graph? Well, remember we said this is the x value that you plug in, and this is the function value or the y value that we get out. So what it means is 2 comma 9 is on the graph. And we can, again, tell just by looking at this function notation, if you plug in a 2 for x, you get out a 9 for y, or the function value. So let's look at the next one. Again, a new name here. So the function is h now. So this is h of x equals x squared minus 3. So we've got an exponent to deal with here. So we're going to find h of 3. And again, it's usually a good idea to plug things in parentheses, especially if there's a negative involved. You notice that I plugged this in parentheses so that we could tell that that was implied multiplication. Here I'm going to make sure that I put that entire base, what I'm plugging in parentheses. So let's see, this is going to be 9 minus 1. So that means h of 3 is equal to 8. And again, it might be a good idea to just ponder for a second, what does that mean about the graph? Well, that means the point 3 comma 8 is on the graph. We'd go over 3 and up 8 units. That point would be on the graph of that particular function. Okay, so remember, we in the last section, we talked about how we could find the domain of a function by looking at its graph. And that was a pretty easy thing to do using the squish technique. But finding the domain of a function just by looking at the equation, that's a little bit more difficult. So what we need to do is we need to remember two things. So there are two operations so far that cannot be evaluated. Now there are going to be some other operations down the road that you're going to run into that don't have answers. But for right now, there's only two of them. So the first thing that we're really familiar is we can't divide by 0. So if you ever see a function that has division in it, you want to make sure that you're never going to be dividing by 0. And then the second thing is we can't take an even root of a negative number. Now we've done a little bit of square root work and cube root work in last year's material. So if you're not familiar with that, you may want to go back and take a look at that. But these are the two, I like to call these domain issues. So if you ever see division, you can't divide by 0. If you ever see an even root like a square root or a fourth root or something like that, we can't take the even root of a negative. Now, if it was a cube root, like say cube root of negative 8, you can do that all day long. So that's not a problem. It's the even roots. And remember, if there's nothing in the little crook right here, if there's no index, remember that's going to be a square root. And we've got a square root down below here. So just keep that in mind. And we're going to take a look at this example 3 here. It says, state the domain using interval notation and then evaluate each function and write your answer as an ordered pair. So we look at this one right here, and again, the cool thing about this is we only need to keep in mind these two issues. If it's got division in it, we want to make sure that we could never divide by 0, and if it's got an even root in it, we want to make sure that we're never going to be taking the even root of a negative. So let's take a look at this one right here. We've got squaring, that's not one of these two domain issues, and we've got subtracting. That's not one of those domain issues. So what that means is we can plug in anything we want, and if you can plug in anything you want, that could be said all reals, or what it means is from negative infinity to infinity. The entire x-axis could be plugged in there. And then we want to find g of 3. So we're going to plug a 3 in here, and again, I'm going to do that in parentheses. So this is going to be 9 minus 3. So we end up with g of 3 is equal to 6. And let's write down the ordered pair. The ordered pair would be 3, 6. And again, that's the nice thing about writing function notation in that form. So g of 3 is equal to 6. The ordered pair would be 3, 6. Let's take a look at this one. This is an absolute value. Now, we don't have to graph this or anything. All we need to do to figure out the domain is if it doesn't have division in it, and if it doesn't have an even root, you can plug in anything you want. You could put any number you want in there, and you could evaluate its absolute value. In other words, its distance from 0, and then, of course, we'd add 4 to that because of this particular function. So we can plug in anything we want, so that would be all reals. That's going to be from negative infinity to infinity. Work on my infinities here, make them look better. And then we want to find f of negative 5. So we're going to put a negative 5 wherever there's an x. So this is the absolute value of negative 5 plus 4. So that's going to be 5 plus 4. So that means f of negative 5 is equal to 9. So the ordered pair would be negative 5, 9. That means that point is on the graph. Okay, not sure what this looks like yet. We may get to that at some point. May get to what this one looks like at some point, but we do know that these points would occur on, or would be on those graphs because they make the functions or the equations true. Now let's take a look at this one right here. This one has a fraction bar, so this is h of x equals x over x minus 2. We've got x minus 2 in the denominator. What we have to make sure of is that denominator cannot be 0. We can't divide by 0. So we look at that denominator and we say, okay, what would make that equal to 0? Let's just solve that. That would be x equals 2. So that's the one number that we can't plug in, because watch what happens. I'd have a 2 on the top. On the bottom, I'd have a 2 minus 2, and then we'd have 2 minus 0. None of that is allowed. So what we'd say here is, you know what, the only thing I can't use is 2. So the best way to say that, especially in interval notation, is to say this. The domain would be from negative infinity to infinity except 2. And the way we say except 2 is we just say x not equal to 2. So if you haven't seen this before, that's how we say not equal to. We just put an equal sign and we put a slash through it. So you can plug in any number you want except for 2. That's what that means right there, x not equal to 2. And then we want to find h of 4. Luckily, that is a number that we can plug in. If this was h of 2, we'd have to say, hey, you can't do that because that's not in the domain. But we're going to put a 4 on the top. We're going to put a 4 minus 2 on the bottom. So we get a 4 on the top and a 2 on the bottom, so that we end up with a 2. So that means h of 4 is equal to 2. So that means the ordered pair that would appear on the graph of this, on the picture of all the solutions, would look like that. Okay, and then the last one, and then we'll do the self-assessment here. We want to find the domain of this function. So this is p of x, another new name. Again, that's how you say that, p of x, equals the square root of x. So let's stop and think about this. This does have an even root. You can't take the even root of a negative number. So for example, you can't do this. You can't take the square root of negative 4. You can't take the square root of negative 1. So we have to make sure that the numbers that we plug in here, the smallest number we could possibly plug in is the first number that's not negative, and that would be 0. So we'd start at 0, and then we can plug in any positive number we want, and we'd have to include 0. So that's going to be from 0 to infinity with 0 included. And then we want to find p of 25. So p of 25, we're going to replace the x with a 25. And we're going to get p of 25 is equal to square root of 25 is 5. So we end up with 25, 5, and that point would be on the graph. Okay, I do want to come back and take a look at one more thing. I'm going to come back up here, and it said, is this a function? Now, in our previous kind of unsophisticated ways, what we'd be looking for is, does each x correspond to only one y? And it does. When I plug in a -2, every single time I'd get a -5. When I plug in a 0, every single time I'd get a -3. So each x corresponds to only one y. But now we can look at this and we can say, well, you know what? There's no division. So we're not in danger of dividing by 0, and there are no even roots here. So the answer on this one is yes, that's a function. It's a function because every time you plug in an x, you get only one y out, and because there's no division and there's no even roots there, okay, which are the only domain issues that we could possibly run into at this point. All right, go ahead and do the self-assessment there, and then good luck on the assignment.